So we're in this chapter 4. We're in this really difficult section or challenging section. It's the simplification of a force and couple system. And we want to solve some problems because I think that's the best way to learn is solve some problems because the theory can be a little dry. So we're focusing today on this force, simplification of a force and couple system. Let's take a look at this problem. It says replace the loading system by an equivalent resultant force and couple moment acting at point A. What is my system? Okay, it's some attached L-shaped object. And how many forces are applied? It looks like there's a force out here, there's a force here, there's a force here. And there are no couple moments applied to the system, just 3 forces at those locations. And they say they want an equivalent system that has a single resultant force and a couple moment acting at point A. So if I conceptually wanted to redraw this system, I'd kind of sketch it like this. And I'd say the 3-force system can be replaced by a resultant force. Maybe it looks like this. And maybe I put the head of the force right there. I could put the tail, the beginning of the force right there too. Some resultant force. That resultant force has some X and Y component. And the couple moment at A. So a resultant force as well as a couple moment, both of those acting at the point A. Now maybe you studied and you said, isn't that a couple moment a free vector? Yep, it is. So conceptually that couple moment could work at anywhere. It could work right out here, and it would have the same effect on the object. It would have the same tendency to make the object rotate. But conceptually we'll just leave it there at both of them apply today. So that's our question. Okay, so how do we approach this problem? Do it by focusing on the forces first, and then focus on the equivalent moment. I would take my time, especially if you're new, but after you get good at it, you can go a little faster. We know the equation is that resultant force that we're going to be looking for is a little vector. In 2D, this is all 2D, so that's easy, just I and J, is equal to the force 1, let's call this one F1 up here. Call this one F2 and call this one F3. So I'll get those 3 forces expressed as vectors and then add them up, and that's my resultant force. All right. So how can I express F1 as a vector? I look at it. They give me a magnitude for F1, 100 pounds. They give me this 3, 4, 5 triangle. And they give me this vector head, and sometimes the vector, the base of the vector shows the point of application, like for force 2. Sometimes the head of the vector is used to show the point of application of that force, isn't it? In this case, the head of the vector, not the beginning of the vector, is used to show the point of applications. So that's showing me the direction. So let me do this. Let me just warm us all up. I would say to take this 100, put it out here. I would put a parenthesis, that's our typical notation used in the textbook for a vector. I would put the units out here just to kind of get them out of the way. And I have something I and something J to finish this out. And can you do that? Basically, I'm asking for the unit vector for that F1. And let me pause, walk around, and let's see if you can do that. What I was looking for is I was looking not only for a 4/5 right here in the I, see the 4 of the 5th, but I was looking for that sign because our traditional X, Y coordinate system, I didn't emphasize it, but often that's the way we run it, and it's in the negative X, isn't it? And we don't want to forget that negative sign. It'll make a big difference. As well as we have 3/5 coming down, And so isn't there two negative signs? There's two. It'll be negative 80 in the I and negative 60 in the J. Pounds. Very good. All right, so let's run with the F2. This one's easy. In the interest of time, it's just 50I and 0J in the units of pound. True. And then the F3 is equal to, and if you did that 3, 4, 5 on the other one, it's pretty straightforward. 150, and you're going to divide by the 5, so that's 30. 30 times the 3 gives us a 90 in the I. And we have 30 times 4, negative 120 in the J. And units of pound. Then the F of R, I encourage you the first time you do it, go ahead and go slow. It'll be the negative 80 plus the 50 plus the 90, all of that in the I, plus the negative 60 plus 0 minus 120 in the J, close, all units of pound. So F of R has an F of Rx of, what is that, 60 in the I? And what is this, negative 180 in the J? And all units of pound. And you could then calculate the magnitude of F of R, which would be 60 squared plus 180 squared square root. That magnitude, about 190. It has more digits to that, but just rounded off the 3 significant digits, F of R is equal to 190 pounds. And then if you wanted to, you could express that vector as the magnitude plus a direction. So if I think about it, it's out 60 and down 180. So 60, 180 down. So maybe what I'll do is I'll make a right triangle, and I'll talk about this angle right here, theta. And then I'll use, like the textbook uses, kind of a horizontal line, and then a line showing the direction of the force, the resultant force vector. And they'll put in here this little symbol theta, and say theta is equal to, I didn't leave enough room, so many degrees. Let me pause, let you calculate theta. I know we've done these things. You're getting experts at right triangles, but I want to make sure. All right, so this one comes in at, 71.6 degrees. One of the things I wanted to do is, I knew some people would want to give a negative sign on that, but because the illustration shows the direction compared to the horizontal in the counterclockwise, in that downward, not counterclockwise, in the clockwise direction, in the downward direction, you would just show it as a positive 71.6. Now, somebody says, what happens if my symbol's like this, and there's theta? Well, then, yeah, you could put theta is equal to negative 71.6. Okay, but this is good like that. Now, to solve for the second part, what is that couple moment acting at point A? What I'm going to do is I'll move to a clean sheet of paper, okay? So I'll move to a clean sheet. And here it is. And so we still have our force 1, 2, and 3. And so what is, just we had for the sum of the forces in the system, we replace it by a single resultant force. The same idea for couple moments, this single resultant couple moment. So what we have is we say sum of the moments that each of the forces generate about a particular point, because A was the point, even though it's a free vector, let's just say about point A. Then what we're going to replace is we're going to replace it by the moment that the resultant force, F resultant, generates about point A, plus the couple moment, and the textbook doesn't really put a symbol on that, but I would just put like C comma A, the couple moment. And we know it's a free vector, so we don't even have to put comma A, or the book puts like parenthesis A. But I think it may help. It's like, what exactly am I showing over here? I'm showing that the resultant force could induce a moment around point A. It doesn't, because my resultant force goes through point A. That's my point of application of it. But if I said put the resultant force somewhere else, it would induce a moment about point A. And then we're asked to solve for this free vector, this couple moment that we can apply anywhere. It's a free vector, but we're thinking about it as being applied to the system at point A. All right, that's a lot to try to explain some of the equations in our textbook, but here, we're looking for this couple moment is equal to, how do I calculate? Well, it's the moment of the force 1 about point A plus the moment that force 2 generates about point A and the moment that force 3 generates about point A. We know that these are all vector quantities, but because we're living and working in 2D, we can do a scalar analysis. I just have to worry, does this force, if I take a look at the force, the third force right here, right? Does F3 induce about point A counterclockwise or a clockwise sense of rotation? I'll have to take responsibility. Yeah, so this line of action goes like that. It's a clockwise, isn't it? Makes it want to rotate clockwise. So I'll have to take ownership of that and responsibility for the direction. All right, if I let's go ahead and work through this then. So we have F1. What does the moment that this force, this is probably the hardest one, F1 about point A. So let's delay that one. This up here was F1. How about the F2? That's probably the easiest one. 0. You're getting really, really good. Now, some students, I'm afraid, are saying, how did they get 0 so fast? So those that saw it was 0, in your own words, why is it 0? Because its line of action goes exactly through A. It can't. So we look, that's exactly it. The line of action of this force goes right through the point A. No moment arm distance. Boom. It's 0. So I could put 0 with any units on it, foot-pounds for units, and I could put any direction, this way or that way. It doesn't matter, or I just leave it 0. Okay. Now let's come over here. This is probably the next easiest, and let's leave the hardest for last. So we have F, the third force right here, and we decomposed F3 into a force which was 90 in the I and negative 120 in the J, did we not? That's a little reminder from the previous page. Okay, can you give me what that moment that the F develops around point A? It's going to be so many foot-pounds either in the clockwise or counterclockwise direction. All right, so we're coming in, a lot of people have it's 360 foot-pound clockwise. And then the book I know is switched, and so they'll put pound-foot, which is awkward for me, but the order of the units in the SI is Newton meter, and it's like both ways out there when you talk about USCS. United States Customary System of Units. All right, this last one is more challenging. What you would do, though, is you look at the point of application of this. You can actually, okay, let me back up. Some people may have said, well, where is this force applied? Is it applied at this point? And then maybe I've got to do an R, come out here with an R, and then an R cross F. Use the principle of transmissibility. Move the point of application of that force back to here. Then decompose it into components. Notice that F3 in the X line of action goes right through A, no moment. And only F3 in the Y induces a moment with a moment arm of 3 foot. Now, this one over here, I could do the same thing. I could have the principle of transmissibility, but then I've got to be accurate and look at where exactly it lands, and it doesn't, I'm not certain where it's going to land or cross. So what I'm going to do is I'm going to decompose it into the F1 in the X and F1 in the Y. I'm showing the correct direction of those two components. And then I notice that, oh, I'm going to have to sum two components here. I'm going to have a perpendicular distance of 1 foot, that moment arm distance of 1 foot for F1x, and I'll have a distance of, and I've got to clean this up a little bit, 3 foot plus 3 foot, or 6 foot, for this F1 and the y. True? Okay. And so what do you pick up? You pick up, for that one, you pick up 80 pound force times the 1 foot, and that's going to make it rotate in the counterclockwise. See that? And then I pick up the 60 pound force times 6 foot, and that makes it want to rotate in the clockwise. So to make them consistent, it looks like I'm working everything in the clockwise. I'll change this to make clockwise, put a negative sign on it. So I'll have 80 minus 80 plus 360, right? 280. All right. Okay, so we have 280, and then we had plus 0, plus 360, 640 foot pound in the clockwise, and that is our, you could put say that's our resultant couple system, or just put the couple moment that needs to be applied at the point A. But that's even redundant because it's a free vector. You can just, there it is. There's the answer. Okay.
So that is a vector?
Yeah, that's a vector.
So you don't need the IJK?
Well, we're doing in 2D analysis, of scalar analysis of this problem. If, like you had it, it would be negative 640, whoops, I think that's the answer you already had, didn't it? In the K only, and nothing in the I, nothing in the J, and then you would be units out here of foot-pound as a vector.
You wouldn't need to specify direction in that sense?
Because it's in the sign, negative sign, yep. It's in it, that has, that conveys the direction. Let's go to 3D, where we have to trust our math a little more. Replace the 2 wrench and 1 force system. Maybe I should put in here 1 force system. So let's find our 2 wrenches and our single force. Well, the single force is fairly easy to find. That's our single force out here, isn't it? And this must be a wrench, and this must be a wrench. What do they mean by a wrench? It has both a force as well as a moment at the same place. And so they say that this has a force of 300 newtons applied at the end of this object in the upward direction, as well as the moment of 100 newton meters at the same location, making it want to rotate. Think again of a screwdriver. You push and turn. You don't just turn without pushing in. So that's the best analogy if you've used screwdrivers. And like down here, it's the same thing. We have both a force and a moment. Hence, you have a wrench. Okay. So now replace that with an equivalent resultant force and couple moment at point O. So everything's going to go back to point O. So what we're going to do is we're going to have a resultant force. Maybe it'll be a force, call it F of R, and it'll be a 3D vector. Here's the answer. I didn't cover it up. All right? That's the answer we're looking for. It's going to be a vector, I, J, K, units of Newton. All right. It lives in 3D. It's going to be, you're going to have to trust our math here. And then we have this couple moment. It's like the equivalent or resultant couple moment that you need to put on the system. And it's a free vector, but anyway, I mentioned this. You think about that also applying at point O, but you could leave it off because it's a free vector. Let's now see that, it's going to have Newton meter, and it's going to be a vector. Okay, so the easy part, and then this is the hard part, isn't it? the equation to calculate that resultant force would be, I need to get my single free force right over here. Let's call this, I don't know if I should call it F1 or F2 or F3. I'll call it F1, fine, F1. And then I'm going to have, don't forget, F2, which is associated with that wrench. I'm going to call that F2. And then I'm going to call this one F3, associated with that other wrench, F3. Those parts of the wrench have a tendency to make the object want to translate motion in the X or Y or Z. So we have to consider it in our sum of the forces. Okay, so I would go slow. What is F1 in an I, J, K? And I look at it, this is not that hard. It's 100 newtons, so I'll put the newtons on the outside. And it's just going to be, here's my X, here's my Y coordinate system, here's my Z coordinate system. So isn't it going to be 0 in the I, 0 in the K, and 100 in the J? And hey, that was easy. All right, let's get F2. Here it is, Newton, and I look at it, and what is F2? How much in the I? 0. How much in the J? In the J, this is straight up. This is my F2, right? Is this aligned with the Z-axis? Is it 100% in the Z? So nothing in the Y, 0 in the Y, right? And then it's just going to be 300 in the K. Maybe I should have gone a little slower on that one. Oh, this one down here is the challenging one. All right, so F3. And this one, okay, what I like to do is I like to think I, J, K. Of those, I can see that it is going to have two non-zero components, but which one is the zero component? There's a zero, either something zero in front of the I or the J or the K for F3? In the J. That helps a lot, I think. So it's 0 in front of the, it resides in the XZ plane. And from the shaded triangle, I could tell this is parallel with the x-axis. This is parallel with the z-axis. Hence, the shaded blue triangle is giving me information that it lives in the xz plane, no component in the y. All right, good. Now I decompose, and I could put, I'm going to run out of room here. It's going to have the magnitude of 200 newtons times the cosine of 45, and then I need to put a sign on that, plus or minus. For the x, it's in the plus. Perfect, thank you. And then I come over here, I'm going to have 200 sine of 45. I didn't leave enough room, sorry, newtons, there's a k. And then I'd say, is it in the positive z, positive k, or negative k? Negative k, so right there. How many places are there to make an error? So many, please. We'll get better at this, right? So we'd avoid errors. Whew. Did everybody follow that? And so then actually you could just calculate the resultant force, and there you go. I'm just going to add the 0, 0, 200 cosine of 45. That should get 141.4. The 100, 0, 0, that should get 100. Yeah, it does. The 0, 300 minus the 200 sine of 45, that gives a positive 158.6. So that was the easy part. Let's move to the hard part again. I look at my system. I'm going to have an equivalent or a simplified or a resultant couple moment applied at O. And so I look and I say, what I'm looking for in 3D has to have the same effect on the system as the moment that the force 1 induces about 0.0 plus the moment that force 2 induces about 0.0 plus the moment that force 3 induces about 0.0, plus the moment that I'm going to say is the couple moment at 2 induces about 0, plus the moment that the couple at 3 induces about 0. These two are components of my wrench. Okay, so there's 5 things I'm going to have to figure out here. Let's work on this one right here. F1, does it induce a moment about 0.0? No. And we can set up an R cross F and we can do all that, but by inspection, its line of action goes through 0.0, it's 0, it's good enough on exam for me. You don't have to prove that. It's by observation because of no moment arm distance. Okay. How about F2 about 0.0? This is my F2 right here. Does it induce a moment about 0.0? Yeah. And I would encourage you could do an R cross F. That R could come in. Let's just talk about it. You could start the R at the origin and go out to the point of application. That's a great R, isn't it? You could also say, principle of transmissibility, I can take the R and come out to point A. And I could do that R, which is a different R, and I could do that cross, the same F, and it would give me the same answer. True? Make sure you do that at least a few times in your life on some homework and check that out. Because the first time you go, how can that be? You're doing a different R, crossing the same F, and you get the same answer? Yeah, that's true. Principle of transmissibility. Now, can you tell that this answer is going to have something in the I, something in the J, and something in the K? It's going to make the object rotate, and this is where I use my right-hand rule, somewhere around the x-axis. Something around the positive y-axis, as well as around the z-axis. But some of those I can look and say are going to be 0 before I jump into the math. Okay, is it this part going to in front of the I, or this part in front of the J, or this part in front of the K for this moment that force 2 induces about 0.0? Can you tell? Yeah, which ones is it going to be 0? K is going to be 0. Why is K? You're right, but why is K going to be 0? Because they're parallel. The force and the axis are parallel. The force that's parallel to the axis can't make the body want to rotate around that axis. Okay, so that's exactly right. All right, let's take a look. Is there another one? Is the component on the I equal to 0, or maybe the component on the J? The component on the J is 0. Why? Because it's not parallel to the J like it was parallel to the K, but its line of action goes right through the Y. And because the line of action goes right through the Y, I have no moment arm, hence 0. So I think looking at the problem and knowing, oh, my answer better be just in the I, then it helps. Also, you can get the magnitude, can't you, in the I? Should it be positive or negative? Use your right-hand rule, put your thumb in the positive X direction, curl your fingers. Is that the sense of direction of rotation that F2 makes it? Yeah, it is. And so I'm going to be looking for a positive something. Is this Newton meter? Yeah, this is Newton meter in the I. All right. Actually, at this point, you don't even put it into cross product. Some of you can get the answer right there. Can you get it? 150. Yeah. Why is it 150? How did you get 150 so fast? You're a miracle worker. Perpendicular distance of a half times the magnitude. A half a meter is that perpendicular distance times the magnitude of 300 Newton. You get 150 Newton meter positive, 150 Newton meter. And really, we did a kind of a scalar analysis to calculate that vector entity. All right. How about this one? The force 3 induces a moment around 0.0. You could do it a couple ways. You could do a scalar. You could actually decompose it this is a 200 Newton of force, right? And I know it's applied here at this point, but it's principle of transmissibility. You could take it back and have it applied at B. And then you would say, I have a component of it in the X, and I have a component of it downward in the Z. True? And then, I know maybe at some point you say, forget it, let's trust the math and do the cross product. But this F3 in the Z will not do anything about the Y, will not do anything about the Z, but it will do something about the I. That F3 in the Z, this will contribute, F3 in the Z will contribute a perpendicular distance of 1.1 meter, and it will be a negative sense of rotation. Right? It makes it want to spin, not in that direction, but the other direction. Okay, because it's forced down. All right, that's the only thing that it makes it want to rotate. How about this F3 in the X? Does it make it want to rotate around the X? No. Does it rotate around the Y? No. Only around the Z. So it's going to contribute, this was contributed around the I, this will contribute around the K, right? And it'll be the magnitude F3 in the X. What its perpendicular distance? The same, 1.1 meter. And does it make it want to rotate in the positive or negative sense? Negative. How many people would have preferred just to set it up as R cross F?
Yeah, that's easy.
A little easier, isn't it? Well, go ahead and do it. But I think this is kind of the extent of a scalar analysis, doing your math for you. All right. All right, what about this one? Let me just clean up the page a little bit. What about this moment that this part of the wrench, this couple part of that wrench, which I'm calling the second, this is 2, how do I express that as a vector? Is this nothing in the I, nothing in the J, and 100 in the K units of Newton meter? Is that what that is? Yeah, that's what it is. And likewise, for the down here for the second couple, or I'm calling it associated with the force 3, that's going to have something in the I, which will be 180 times the cosine of 45 in the I, right? And then I'm going to have to write it in the J, 0 in the J, and then in the K, minus 180 sine of 45 in the K, all having units of Newton meter. All right, so now I did a lot of work, but I express all of these 5 entities as vectors, and now I sum those 5 vectors, and there's my resultant. And that's the answer that we were looking for, which is what is an equivalent couple moment applied at point O. See, it's equivalent resultant force and equivalent couple moment at point O. All right. Well, it looks like I'm out of time. I thank you for your attention. Grades are posted in Gradescope. If you have any trouble getting your grade or finding your grade, please visit me in my office. We'll work through it together. Okay? Thank you for your attention. Next week, Friday, we have an exam.